Hey guys, and welcome. In our last video, we found the required section modulus in the required area for this gable roof to work. And what we got 2x6 member working, a Douglas for large number 2 2x6 uh, roof rafter to work. Now, even though it's working for when it comes to shear moment, we also have to check for deflection. So we're gonna do that now for this video. We're gonna check for the deflection limit and see if the 2x6 are good. We're also going to find the thrust in the ceiling joist and connect the ceiling joist to the rafter um, using some 10 penny nails. So let's do this. Let's fast forward over here. So again, this is where we left off. We have a 2x6 working uh, for 1 minute shear. So now we're gonna check if it also works for the deflection limit. So here we have roof members, and in this case we're gonna have someone live in the attic, and so what's gonna happen is there's gonna be some jip on the rafters, and we don't want the rafters to be deflecting too much. If it does, then it's gonna cause some problems. It's gonna cause some cracking in the jip. So here we have the deflection limit for snow, which is all over 360. So the rafters is a simply supported beam. So the maximum deflection for a simply supported beam is just 5 times the uniform load times the length to the fourth power, all over 384 times the Young modulus times the inertia. All right, and that you want that to equal to all over 360. So this is for snow. So now if we rearrange this, we could find the required inertia for this. So I require for snow is going to be 5 WS times L to the third divided by 384 times E, and then we're going to multiply this by 360. Same thing is going to happen to the dead plus snow. This is a different loading now. So this I'm going to call this WT, that's the total load. So if we plug everything in, let's do for the I require for snow. I believe this is 32.6 for the snow load, the uniform load, linear load. Now this is in pounds per feet. So we want to convert this into pounds per inch. So we're going to multiply that by 1 foot over 12 inches. So the feet are going to get canceled. We're going to have it in terms of pounds per inch. Now we have 12 feet, and we want to convert this 12 feet into inches. So in 1 foot is 12 inches. So the feet get canceled. This is going to be to the third power. Divide that by 384 times the Young modulus for our Douglas for large number 2, and then we're going to multiply this by 360. When you plug all this in, you're going to get an inertia, required inertia of 23.76. Okay, and you do the same thing for the dead plus snow. The only difference is that this is going to be 51.45, and then this will change to 240. So that's the only difference. So when you do that, when you change when you change the uniform load, and when you change the L over 360, in this case will be the L over 240. When you change the 360 to a 240, you're gonna get a required inertia of 25 on the dot. All right, so this is what's gonna control. My question is a 2x6, does it have enough inertia? So inertia is just B times D to the third power over 12. So for a 2x6 member, it's just 1.5 times 5.5 to the third divided by 12. When you do that, if you plug that in your calculator, let's see what we get. We get 20.8. 20.8 right here is much less. It's less than 25. So the 2x6 member is not going to work. It's no good for deflection. So I wouldn't use 2x6. And in fact, you won't. Maybe in old homes you'll see a 2x6 members, but for new buildings or new houses being built today, architects would like to go with a deeper beam. They would like to go with even. They might not even want to go with a 2x8. They probably go with 2x10s or 2x12s rafters, due to insulation purposes. They want to insulate the house. They want to keep it warm and greener. So they'll go with 2x10s probably, most likely. So let's see what 2x8s are. I'm sure 2x8s will work. So 2x8, the inertia for a 2x8, I think is 47 inches to the fourth. And again, you use 1.5 times 7.25 to the third power divided by 12. And I believe you get something close to 47 inches to the fourth. So 2x8s will work. So let's just stick with 2x8s. Where's this? So now we're gonna take care of the thrust. Okay. So let's find the thrust in here. So we took care of the rafters. The rafters are good. We have 2x8s at 16 inches on center. Let me write that down. Let's say they're gonna spray foam insulations there, so we are okay with 2x8s. So now we want to find the thrust here. So to find the thrust, let's see if we could do this. Maybe not. Doesn't let me. Have to dry it out. All right, that's fine. So I have this right here. We're gonna calculate for the thrust. All right. So we have here some kind of loading here. We have here our horizontal load, we have vertical, horizontal. So then this has to be some kind of load going this way. We also have the load going down. This is 51.45 pounds linear feet. This over here, this height is 12 feet. This over here is also 12 feet. Let's call this point A. So what we're gonna do is we're gonna sum the moments at A, and the summation of moments at A has to equal to 0. Okay, so let's say clockwise is negative. Let's just say that. So let's sum the moment A. So what we have here, we have 51.45 times 12, and that's gonna give us our loading going down. So we have 51.45 times 12. That is our load. Okay. And then we have to multiply by that distance. So that's going to be half of 12 is 6. And then this is turning clockwise. That's going to be negative. Now, what we have here is we have a force going this way, which we want to find. Plus, let's say H is the horizontal thrust that we're looking for, times the height, which is 12. And this is going counterclockwise. It wants to rotate counterclockwise, so it stays positive. And that equals to 0. So if you solve for H, in the end, if you solve for H here, let me see, I'll do it. We have 6 times 51.45 times 12. That gives us 3,704. Negative 3,704.4 pounds feet. That equals to negative 12 h. We divided by negative 12 both sides, and this is actually feet, so don't forget that. So in the end, we're going to cancel out the feet. So if you divide that by negative 12, the horizontal thrust is 308.7 pounds. So this one, there's a tension. This member right here, this ceiling joist is in tension. So the tension there is 308.7 pounds. All right, so that's good. So now that we have that, we could find out how many penny nails do we need in order for this to work, in order for the thrust to be taken care of. All right, so what we're going to be using, we're going to be using the NDS National Design Specification for Wood Construction. All right, the manual. And you go table 12N is for nails, right? And you're looking for, what we're using is Douglas fir. So we have this right here, Douglas fir. And we're using 10 penny nails. That's what we want to use, 10 penny nails right here. So if you make your way to the right, you could see here that this is 116 pounds. So our Z is 116 pounds. So our thrust is 308 pounds. And then our Z here, this is 116 pounds per nail. Now remember, we could also use the duration factor. The duration factor could also be used for connections. So if we multiply this by 1.15, because we have snow here, it's gonna reduce the number of penny nails. So we have 308 divided by 116 divided by 1.15. You're gonna get 2.3 nails. So we go with 3 10 penny nails. So that will take care of the thrust. So again, if you go back over here, if you go back to this drawing over here, there's gonna be 3 and 3 10 penny nails to connect the rafters and the ceiling joists together. All right, so that's good. Now we also have the ceiling joists. We're gonna have people in the attic. So let's say this is our ceiling joist, and we're gonna say there's a bearing wall or there's something here breaking this up. All right, because we want to use a bearing wall. There's gonna be a girder. Let's say on the first floor there's gonna be a girder around here to pick up the bearing wall. So let's say there's a bearing wall. All right. So this is 6 feet. No, excuse me. That is 12 feet. All right, 12 feet, 12 feet. We're gonna find the capacity of the ceiling joist. So let's find let's just say the dead load for the attic here is 15 pounds square feet, and let's just say the live load here, let's say just bedrooms, is 30 pounds square feet. We multiply this by 1.33 by 1.33 to get the uniform load. So it's gonna be 20 pounds linear feet, and then our live load is going to be 40 pounds linear feet. We add those two together, that's going to give us 60 pounds linear feet. So that our maximum moment is going to be WL squared over 8, which is 60 times 12 squared over 8. That's going to give us 1,080 pounds feet. And V maximum is going to be WL over 2. That's going to give us 360 pounds. And then we'll do this. Then just do the same thing. The same thing that you did for the rafters, you do the same thing for the joists. You want to find the required section modulus. You want to find the required area for the ceiling joist to work. And in the end, I did the math. I have 2x10s working. The 2x8s doesn't have enough section modulus, so I'm going with 2x10s ceiling joist. So yeah, it's the same process. So I don't want to bore you guys doing the same thing over and over again. So it's the same thing. Fine. I mean, go back in the video. It's it's same thing again. Just go back and I think the second video and just find the maximum moment, maximum shear, and then find the required section modulus, find the required area, and then also do the same thing for deflection. I have the deflection also working for the 2x10. So 2x10 city joist is good to go. Now, how are we gonna connect? So let's say the ceiling joists are this way, they're overlapping over the bearing wall. All right. So again, there's thrust here. There's 308 pounds of thrust. So in order to take care of this, we could just use 3 10-penny nails, and that'll take care of it. Because we did it earlier. We did the math earlier. It worked for the the connection between the rafters and the ceiling joist. So it will also work here too. If I use 3 in the other portion of the ceiling joist and rafters, then it will also work in the interior portion of it too. So 3 10-penny nails will work. Now, let's say you don't have that. Let's say you have your 2x8 ceiling joist. You have a hanger, and then you have a beam over here. Okay. These are my hangers. Again, you still have that thrust, 308 pounds of thrust. So you need to take care of that. So if you have a hanger, you just go to the Simpson Strong Tie. Use their catalog. I have 2x10s. So let's say you're using LUS 210. All right, you want to find out if you want to take care of the withdrawal values. So what we have here, we have 8 10-penny nails going from the face of the hanger to the wooden member. You have 8 of those guys. And then you also have 6 going through these little holes over here, and it's gonna be toenailed. But let's just forget about that now, because I think just 8 of the 10-penny nails has enough capacity for the 308 pounds. So I think that's gonna be good. So I'm gonna show you guys how to do that real quick, and then we'll be done with this video. I think we'll be done on the analysis and design of the gable roof. So you go to the NDS and you go to the table 12.2C, and what we have here, we have Douglas fir large, so that specific gravity for that is 0.5. The diameter for 10 penny nails is 0.148, and that's what they use for the Simpsons. They used 8 10 penny nails. So right here, the withdrawal value is 36 pounds per inch. So how much does it penetrate within the wood? It's going to penetrate, let's say, 3 inches. The 10 penny nails are 3 inches long, so it's going to penetrate 3 inches. So 3 pounds per inch times 3 inches, that's going to give us, let's see if I put it down, 108 pounds. And there's 8 10 penny nails. So if you multiply 108 pounds times 8, that's going to give us 164 pounds. So the hanger itself has enough capacity for withdrawal, has enough strength, so it's good. So a quick recap for this video. It was pretty long, and I apologize for that. We found out that the 2x6 could work, but we want to find out if it's also good for deflection. We did, and the 2x6 is not good for deflection, so we went with 2x8 rafters. Then after that, we also have to take care of the thrust. So we found out here that the thrust here is 308.7 pounds. So in order to connect the rafters to the cylinders, we're going to use 10 penny nails. So we want to find out how much penny nails do we need. So we use the table 12N. Our Douglas for large is specific gravity is 0.5. Our 10 penny nail is 0.148. You come over here, you have 116 pounds. So math, in the end, we got 3 10 penny nails to work. Now, if you have the member, if you have a bearing wall and the member is something like this, then you only need 3 10 penny nails. If it looks something like this, if you have hangers and you have, let's say, a beam, then you have to check if the hanger itself has enough capacity, withdrawal capacity. So you find out how many penny nails are going through the face to the header or the beam. We have 8 here. We go to table 12.2c. Specific gravity is 0.5. 10 penny nails. So the withdrawal value is 36. And you just do your little math here. We have 864 for capacity. That's good. And I think that one thing I forgot to mention is we want to find out the cylinders, what it's going to be. So in the end, we found out that the cylinder is going to be 2x10s cylinders at 16 inches on center. So I think that's it. I think I mean there's hurricane ties that we have to take care of too, but I could do that in another video. How to calculate for the wind loads and uplift and take care of that. So again, I hope you guys enjoyed. Hope you guys were able to learn. Hope you guys understood how to design and analyze a gable roof system. And if you know how to do this, then you can apply it to other kinds of roofs. It's very similar. Again, thank you and have a great day. Bye bye.